All right, in this video, we will be writing an inductive proof of the sequence that you see up on the board here, on the display here. And again, this is exactly what we started with earlier. This is the same one that we explored a little bit earlier. The sequence 1, 3, 5, etc., 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 generated by the equation a sub n 2n minus 1. And the conjecture is that n squared finds the sum of n terms of this sequence. We're going to prove it algebraically. So, first thing we're going to do is the anchor step, where we're going to show that the formula works. The conjectured formula works for a specific value of n. We've done that. We've done it plenty of times for this particular sequence, but we're going to repeat it for sake of completion in this particular example. So I'm going to choose n equals 4. That is 100% arbitrary. In other words, you can choose any number you want. You can choose 1, you can choose 2, you can choose 1,000, whatever you want. Completely arbitrary. So what this is saying is take the first 4 terms, 1 plus 3 plus 5 plus 7. Is that equal to 4 squared? In other words, here's the first 4 terms. This is the sum of the first 4 terms. Is this equal to this equation with 4 plugged into it? And sure, it absolutely is. 1 plus 3 plus 5 plus 7 is 16. 4 squared is 16. So yes, it absolutely works. The anchor step is a big old check mark in this case. Okay, so let's get into the actual meat of this problem. Let's actually get to the proof. And here's how we're going to do the proof. This was written on the how-to page at the very end of the first part of this lesson. But this is the algebraic portion of the proof. And the big thing to take from this is we've got two things going on. We've got 2 equations going on. We've got the A equation, which is the sequence itself. It generates the values of the sequence. And we've got the S equation, and that's this. And this S is this S, this S is this S. So these guys are all S's. And this guy here, these are the A's. So color coding is good, so hopefully that will help you out. So let's check out what's going on here. I got S sub n, and I want to add to it A sub n plus 1. I'm going to start off with the S sub n. S sub n is n squared. And now, take the A, take the sequence generation, and this is 2 variable minus 1. Because that's what this says essentially up here, 2n, 2 variable minus 1. So what I want to do, though, is instead of just being an n, I'm going to plug an n plus 1 in here. And now I am going to simplify the heck out of this. Not really too much going on in this particular problem, but whatever simplification is possible, you do. So all I did here was distribute. And now combine some like terms and we get this. And on this side of the proof, we are done now. There's nothing else we can do. We can't simplify it in any way. So we're going to hold that thought and turn our attention to this problem. So now I want to take S and do the same n plus 1 thing to here. So S says variable squared. Variable squared. But instead of just an n, I'm going to put an n plus 1 in its place. And I'm going to simplify. And cross my fingers and hope that this simplifies to the same as this does, which it absolutely does. If you're savvy enough to have factored this already, you would have seen that it's n plus 1 squared. But I digress. Don't forget to not distribute the square. Don't forget to properly square this binomial. N squared plus n, right? The whole FOIL thing. And the fact that we got these two things to match is the hooray moment of an inductive proof. These two things match. And that's the big idea here. These two things match. We took this expression and we said it in two different ways. We added n plus 1 terms together. The first way, we took the sum of the first n terms and added the next term, and then we found the sum of the next term. Those two things are matching, which means, what does that mean? That means that n squared represents the sum of n terms of the sequence 2n minus 1. So what that means is, when all is said and done, the sum from 1 to n of 2n minus 1 is n squared. And we have just proved that that will work every single time.